constellation Libra, a faint point of light races through our galactic neighborhood. It looks ordinary through a small telescope. Yet when astronomers calculated its age, the result appeared impossible. The universe is about 13.8 billion years old. This star's estimated age once came out near 14.5 billion years. A star older than the universe would not merely be surprising. It would break the story of cosmic history. No stars could exist before space expanded, matter cooled, atoms formed, and gravity gathered the first gas clouds. So either cosmology was wrong, stellar physics was wrong, or the number was being misunderstood. The object is HD 140283, widely known as the Methuselah Star. Its apparent paradox became one of astronomy's best demonstrations of how scientists measure ages they can never watch directly, and how an uncertainty can transform an impossible claim into a powerful clue. HD 140283 lies about 190 light-years away, close by galactic standards. It is not one of the universe's first stars, but it belongs to an ancient population that formed when the Milky Way was young. The clue is motion. The star moves rapidly relative to the Sun on an elongated path through the galaxy. Behavior associated with the Milky Way's old halo population, rather than the younger, flatter disk where the Sun lives. The deeper clue is chemical. Astronomers call elements heavier than hydrogen and helium metals. HD 140283 contains very little iron compared with the Sun. That chemical poverty reveals an early birth. The universe began mostly with hydrogen and helium, plus traces of a few light elements. Carbon, oxygen, iron, gold, and most of the periodic table were manufactured later inside stars and stellar explosions. A star born before many generations had lived and died should contain fewer heavy elements. HD 140283 does. But it contains some metals, which means it cannot be a pristine first-generation star. At least one earlier generation enriched the gas from which it formed. No astronomer can cut a star open and count rings. Stellar ages are inferred by comparing observations with models of how stars evolve. The first measurement is brightness. To know a star's true luminosity, not just how bright it looks from Earth, astronomers need its distance. A tiny shift called parallax provides that distance. As Earth moves around the Sun, a nearby star appears to move slightly against the more distant background. The Hubble Space Telescope measured HD 140283's parallax with high precision. Once astronomers had a better distance, they could determine its luminosity more accurately. They also measured temperature, chemical composition, and evolutionary state. HD 140283 is a subgiant. It has begun leaving the long, stable phase in which a star fuses hydrogen in its core. Subgiants are valuable cosmic clocks because their brightness changes rapidly compared with most of a star's life. A small change in the model age can produce a measurable change in luminosity. Researchers then compare the observed star with theoretical evolutionary tracks. Where its temperature and luminosity intersect, a model track gives an age estimate. The result is not a date stamped on the surface. It is a probability built from measurements and assumptions. A widely reported Hubble-based analysis estimated an age of about 14.5 billion years. The headline practically wrote itself. Astronomers had found a star older than the universe. But the estimate included an uncertainty of roughly 800 million years. That uncertainty is not decorative. It represents a range of plausible ages produced by errors in distance, chemical abundance, temperature, and stellar modeling. Subtract the uncertainty from the central value, and the star's possible age overlaps the age of the universe. The result created tension, not a logical contradiction. Imagine measuring a table as 201 centimeters long with an uncertainty of 3 centimeters, then discovering the room is 200 centimeters wide. You have not proven the table passed through a wall. You have learned that the measurement needs refinement. Later analyses using improved data and different modeling choices generally place HD 140283 at a younger age, often near 13.5 billion years. With uncertainties that continue to overlap cosmological limits. The exact value depends on which physical inputs are adopted. The sensational phrase, older than the universe, survives because it describes one central estimate while ignoring the range around it. Distance is only part of the challenge. The models themselves depend on physics that cannot always be measured perfectly. One important input is oxygen abundance. Oxygen changes the rate and pathway of fusion in an aging, metal-poor star. A different measured oxygen abundance can shift the inferred age by hundreds of millions of years. Another input is how helium and heavy elements slowly settle inside the star through diffusion. Convection, mixing, nuclear reaction rates, and the treatment of the outer atmosphere all affect where a modeled star appears on the age track. None of this means the models are arbitrary. They are constrained by laboratory nuclear physics, observations of the sun, star clusters, and thousands of other stars. But a billion-year error is only about 7% of a 14 billion-year estimate. At the edge of cosmic history, a modest percentage becomes an enormous span of time. The apparent paradox is therefore useful. It forces astronomers to inspect every assumption capable of moving the clock. The age of the universe comes from an entirely different method. Cosmologists measure the expansion of space, the cosmic microwave background, and the contents of the universe, then use a cosmological model to calculate how long expansion has been occurring. The standard result is approximately 13.8 billion years. That value also has uncertainty, and debates over the present expansion rate, the Hubble tension, show that cosmology is still being tested. Yet no mainstream measurement gives stars permission to form before the hot early universe cooled enough for matter to assemble. Stellar ages and cosmological ages therefore check each other. If many well-measured stars reliably exceeded the universe's age by a large margin, the conflict would be serious. Instead, the oldest stars and clusters approach the cosmological age from below once uncertainties are treated properly. That agreement tells us something important. Stars began forming remarkably early. HD 140283 probably formed only a few hundred million years after the Big Bang. It may have originated in a smaller early galaxy that was later absorbed by the growing Milky Way. It is a surviving fossil from the era when the periodic table was still being assembled. Its small supply of metals records material made by stars that lived and died before it. Those earlier stars may have been massive, short-lived, and chemically primitive. HD 140283 is therefore not the oldest object in existence, and it is not known to be the oldest star. Other ancient stars and globular clusters compete for that description, and new surveys continue to find metal-poor candidates. Its importance is different. Because it is relatively nearby and bright enough for precise observations, it gives astronomers an accessible laboratory for testing the lower boundary on the universe's age. The Methuselah Star did not overturn the Big Bang. It taught a more valuable lesson. Scientific measurements are not single perfect numbers. A responsible result includes the range that the evidence allows. Remove that range, and an ancient star becomes an impossible object. Restore it, and the contradiction becomes a conversation between two independent clocks. One clock is written across the sky in the expansion of the universe. The other burns quietly inside a nearby metal-poor star. They do not tick in exactly the same way, but both point toward the same astonishing conclusion. The cosmos formed stars almost as soon as it was physically able to do so, and a few of those early lights are still shining close enough for us to read their history